So now we've looked at operating systems and what they are, let's have a look at the type of job that they do. And there's a number of different jobs that they do. So we're going to have a look at things like how we access the disk access and the file management, a quick look at device drivers. We'll have a look at networking, which is ever so important these days with the internet. And then with that, along with that, security. Then we'll talk about user interfaces, and finally we'll end up with a graphical user interface. So I'll try and keep it simple and try not to go into too much detail. And I've got some notes that you can refer to and look at another time. And now we come to one of the biggest abstractions of the lot on computer systems, and that's the way that we access our disks and we manage our files. To us, they look like folders and directories and files. They're nothing like that behind the scenes. They are blocks of memory on a hard disk or on some sort of external storage. But an operating system takes this and gives us an abstraction that we understand, which is file management. And basically, any file that's stored on disks or external storage use files. And those files are actually structured for faster access, high reliability, effective use of the driver's available space, and the file system or the file system directory tree represent this structure to us, even though that's not what's actually happening behind the scene. Now, in the early file systems, they were limited in terms of their capacity, their speed, the length of file names and the type of characters you can put in file names, the directory structures they could use, and really it reflected limitations of the operating system, because now we've moved a lot forward. But in the early days, it was Unix and Linux that supported this technology called virtual file system. And it supports a wide variety of storage devices, regardless of their design or the file system. So we had to create something that was abstracted and something that could work on many different types of system. And it was accessed through something called a common application programming interface. We've all come across these. We know them now as APIs. So we have a set of APIs, application programming interfaces, that need no knowledge about the device they're accessing. They have a standard way of operating and they don't need to know exactly how that particular device works. And this virtual file system service allowed the operating system to provide the program with access to an unlimited number of devices with an infinite variety of file systems through the use of things called device drivers and the file system drivers. So for every particular technology, they would create a particular device driver that worked for that particular technology and could talk to the file system drivers and do the job no matter what device was on there at the other end. So the storage device is accessed by the device driver, and the device driver is written by the manufacturer of the actual device, and it understands the specific language of the drive. So it knows how the drive works and how to put it in, and it's able to translate that language into a standard language that's used by the operating system, which is our file system, and allows access to all the disk drives. And on Unix, this language is referred to a language of block devices. So it's a marvelous piece of work there to be able to work with any types of different systems. So in our disk access, we have a device driver that allows the kernel to access the contents of the disk drive. The file system driver is used to translate the commands so that the operating system can talk to all the different filing systems. Programs can then deal with these filing systems on the basis of their file names and their directories and their folders. So it gives us this abstractions of files and directories. Now, the various differences between the file systems make supporting all file systems very, very difficult. You can imagine the different manufacturers of different type of devices that are out there. You know, for example, what type of characters are allowed in there? What about case sensitivity? What about different attributes that we can give to all these things? And we have to have some sort of single interface to apply to those. But, you know, we've got around that and that works. Now in Microsoft, we've got support for file systems. It's very, very highly varied depending on different types of system. Windows, for example, only uses the format of NTFS. It's the only file system which the operating system can be installed on. However, when it comes to things like Linux and Unix, it can support many different other filing systems. So any system can be used as far as they're concerned. Although with Windows, we're limited to the NTFS type. And how does it all work? Well, we have our application that executes the input-output statement. That then goes to something called a logical file system. It's a usually directory structure to provide the file organization module within the information. And then we've got a file organization which handles their file and their physical blocks, i.e. where they're going to be stored. Then we have the physical file system that actually issues the input-output commands to the actual device drivers to read and write those particular blocks. And then we have our input and output control. These are our device drivers and our interrupt handlers that we spoke about earlier on, which then put all this information and pass it on to the devices. So we have a lot of different layers there working together to actually be able to provide us with this file type of structure and to allow applications to access all that information. And a lot of it's abstracted away, just like the zeros and ones in machine code. So central to all this are the device drivers. So what are device drivers? Well, it's the bit of code that we have to download whenever we find having add another piece of hardware to our computer, we have to have a device driver that can talk to that, whether it's a mouse, a keyboard, a printer, and it's software that's developed by the manufacturer to allow interaction with this hardware device. And the idea is it provides commands that go to and from and receive data to and from the device on the other end. And that means we need a specific interface to the operating system and the software application. So we have specialized hardware-dependent computer programs that actually allow us to talk to the particular hardware we want to talk to and give us some sort of transparent interaction with that hardware device. And of course, there's a user abstraction there. The operating system can't be expected to know how to control every single device driver, every single different application. And if we have different devices and then we have different variants of that particular device, it can't know how to run all of these. So the operating system essentially dictates how every type of device should be controlled. So there is a standard way that the operating system will work with these things. And then the device driver translates those operating systems mandated functions into the device specific calls. So we have our certain set of rules and the way that we're going to work with you, and it's up to the device themselves to implement and talk in the language that the operating system can understand. A bit like, the USB connections. As we said before in earlier days, that we used to have all sorts of different ways of connecting to a computer, serial ports, parallel ports, but then they came up with this one USB way of connecting up. So every manufacturer now must write according to a USB. Likewise with the code inside. There are certain standard protocols, certain standard ways of talking to the operating system that the operating system enforces, and it's up to the people who create those device drivers to ensure they stay with those rules and regulations. So we have a new device, then a new driver ensures that the device appears to operate as usual from the operating system's point of view. And it's all made so much simpler these days because you can plug into a Windows application and it will a Windows operating system, and not only will it know that you've plugged something new in, but it will go off to the internet and find a particular device driver and download it and connect it without you having to even know that. Wonderful. Not like the old days where we had to go and find the disks and load the disk on, tell the operating system it was there. Things are made so much easier. So as we can see from the diagram, we have the application that talks to the operating system. The operating system then talks to a particular device driver. If it could be for a mouse, it could be for a speaker, it could be for a printer. And remember, we talked about interrupts. So if these things want to do anything, they will send the interrupts, and then the operating system will say, okay, off you go and do something. So there's a lot of this communication going on, and our device drivers allow us to communicate with the operating system. Now, one of the things that's so important these days is networking. And networking's everywhere because we have to be able to interact with the internet. That's one of the big things. Then we have things like Bluetooth. Then we have things like Wi-Fi. So we have to be able to talk to other machines, and other machines talk to each other. Not like the old days where we just had loads of cable plugged into each other and we couldn't do it, and then there wasn't even any internet, or we had a phone line. So most operating systems support a variety of different networking protocols and different hardware applications. So what do we mean by a protocol? Well, a protocol is just a set of rules. So each thing needs to know how to talk with each other. Remember, at the end of the day, it's all zeros and ones. And if you just get a whole load of zeros and ones thrown at you, how are you going to know how to deal with them? So we have protocols, ways of putting these together, these zeros and ones, in a way that things will understand. So computers running, the thing about networking is you can have computers that are running different operating systems, but they can participate in a network. So they can share resources such as printers, files, scanners, or different wireless connections. Networks allow a computer's operating system to access the resources of a remote computer as if it was connected directly to that particular computer. You know, very simple communications, using some sort of network file system, sharing another computer's graphics or sound hardware. We had things like Secure Shell that allows network users direct access to a computer's command line interface. You know, so it's not very unusual these days. If you've got a problem with a computer and you call somebody up and say, let me just link up to your computer and I'll do things, and then magically watch that mouse move around the screen and things happen. But that's what we can do. So we have client-server connections. So a client will connect to a network through a particular server. And servers basically offer various services to other network computers. That's why they're called servers, because they provide services. And now these days we talk about things like cloud services, which provide these services to users. Even software now is software as a service, which means that we can go off and not have it on our machine, but we can use software that's been run somewhere else on a different server. How does it do that? Well, it usually uses things like ports, and each application can link up to one particular port, and that application can then use all the communication through that particular port or receive any information from that particular port. You know, and we use things like IP addresses as well, if you're familiar with the internet, and we can talk about that on a different section a little bit later on. So each port number is associated with one running port, and there's something like 65,553 different ports that we can use. And you know, this is where a lot of people try to get into other people's computers, and you'll be surprised at how many programs constantly on the internet are searching for ports on people's machines that are open. And the idea of a port is it's really there responsible for handling requests to the application, and the application handling requests to the port. But we've got to bear in mind that one of the reasons why people try searching through these ports for a way in is because once you can get in, you can use the local hardware resources just by sending requests through that particular kernel system. And that's really how some sort of malicious code can work. It can sit on your computer, it can listen to what you're doing, and it can send information back out through a port without you even realizing that's going on. So these days we're talking about cloud services, and more we're turning now more to cloud services, but this now means about always on computing. And you're going to see a big change here now as 5G is developing. We can have not only constant connection but also very fast connection, and so that's the way that we're moving more and more to a whole connected world, as we've seen already. Now, of course, vital to all this is security. When your computer's open and when you're talking to so many different places and so many different networks, security becomes an important thing. And a computer being secure depends on a number of different technologies that are working properly. And the idea is we need to provide access to a number of different resources that are available, and software that's running in the system, even to external devices, things like networks via the kernel. So we must be able to distinguish between requests which should be allowed to be processed and others which should not be allowed. And we generally use things like authentication and authorization. And that, as you've probably seen, is username and password. Although, these days, I think we're going to begin to see the end of passwords and look more like biometric data instead. Already on phones, you can do fingerprint type of recognition, and I can imagine that to becoming more and more as time goes on. So we can use things like magnetic cards, biometric data, things like fingerprints, eyes, facial recognition, and then the resources can be accessed through this authentication. Once you've authenticated yourself and you go through, sometimes you're allowed to use other various parts of that system because you've already been authenticated somewhere else. You can have some access that can be accessed without authentication. Things are trivial, maybe things like maybe reading files over the internet, but where you don't actually make any big changes. Particular service and resources that are accessible by the requester, once they're logged into a system, are tied to the actual authorization that's gone on. So once you've authorized yourself and gone through, then that you can be allowed access to other things based on what you've already, the way you've already authorized and authenticated yourself. What's the difference between authentication and authorization? Well, authentication means you are who you say you are. So you have to make sure that you are that person. And then authorization, well, you as a person might be part of a group, or might be just you individually, but then you have to look at what you've actually been authorized to do. You might be able to access a database, but you might not be able to change anything in the database because you're not authorized to. So authentication is identifying that it's you, and authorization is really letting you do the things that you're supposed to do. And we can have things like auditing options. Why? Well, because we have this thing called non-repudiation. What does that mean? Well, we don't want people to be able to turn around and say, oh, it wasn't me. So we have this ability to trace things back and audit and see who's done what, which is important for security. And all the requests carried out through these interrupts to the operating system. If the programs can directly access hardware and resources, they can't be secured. So we have to access it through an intermediary that can check to make sure that we're not doing anything we're not supposed to be doing. So you can have things like external requests from an outside computer, and it can be checked. So they pass through device drivers to the operating system's kernel, where they can be passed into applications. So we have to go through that kernel first of all to check and make sure that what we're doing is secure. Security of our operating system is a major concern, to everybody, because if we've got our banking details, financial details, and documentation from people who don't want other people's non-disclosure type of agreements, we have to make sure that we are secure. Network services can include things like file sharing, print services, email, websites, and even things like file transfer protocol if we want to take one file and put it somewhere else. So obviously we have to make sure these are secure. Now, one of the chief ways of making things secure, our system secure, is using things called firewalls, or some sort of intrusion detection system. And now most modern systems have some sort of software firewall which we can enable, and they are enabled by default, and we can add and change it to as we want. And we can configure it to either allow or deny traffic depending on who it's coming from and the different type of services and the different port. There is another strategy that can be used and has been seen used, and that's called the sandbox strategy. And that is where the operating system will give you a certain part and say, right, you can work in that, but you can't come out of that. Java uses that to a certain extent when we were looking at things like Java Beans. And then we'd have to look at things like internal security for multi-user systems. So if we've got a system where a lot of users are using it, then we have to give each user some sort of ability, and certain groups of users the ability to do other things. So each user of the system can have access to private files that other users can't play around with or read. And you need some sort of internal security, and we also need auditing so we can track and trace what everybody's doing. We don't want anybody to potentially bypass an operating system. Security is a big issue, and it will get bigger and bigger because there are always people looking to exploit that security for various different reasons. So finally, we come to the user interface, and that is where we work with the computer. And usually that's the source of a lot of frustration for a lot of people. But every computer that's going to be operated by an individual requires some sort of interface. And the user interface is usually referred to as a shell, but it's essential if people are going to work with computers. So what does the user interface do? Well, it views the directory structure, so it allows us to look at the directory and gives us this abstraction of a directory structure. It requests services from the operating system that will acquire data from input-output hardware devices. So, keyboard is obvious. If I type things into the keyboard, how is the computer going to translate that? Through the user interface. And if it's going to put something onto a screen so I can read it, how does it know? Through the user interface. It takes things like the mouse clicks and it reads them. Credit card readers, anything you can think of where we have an input, then the user interface deals with that. It also requests things like operating system services. Tell me what's going on the system. Show me a picture of what I've just printed. So input and output are very much down to the user interface. And there's two most common forms of user interface, and that is a command line interface and a graphical user interface, which has this WIMP standard. What does that stand for? Windows, icons, mice and pointers. So in the old days, we had command line interfaces, and you can see an example of a command line interface such as Microsoft DOS, and you can still work on that command line. Now with Unix, people very much use a command line rather than a graphical user interface. And we also see a graphical user interface, one of the earliest from Apple, that was on the Mac, that gave us these pictures of files and a file system, and we had a mouse and a pointer that we could go around and click. Most people prefer to have something visual and something to click with a mouse and not have to type things in, because typing things in means you have to remember the commands that you're using, and that can get quite complicated. So we have the birth of the graphical user interface and how we interact. Now, of course, this is going to change more and more. The way we act with computers, now we would start doing things like touch screens, which we didn't used to have. Soon, maybe we'll be able to do things like point, and certainly if you look at virtual reality, you can use your finger as pointing. Things like the Wii game, the Wii station allows you to actually move around and it recognizes movement. Things like Microsoft Kinect. So user interfaces are not only have to be graphical, but graphical is the first step there. And in modern days computing, graphical user interfaces are actually integrated into the kernel. In the early days, it was an add-on. It wasn't the actual operating system itself, but these days it adds to put it in there. So it's technically not an operating system service, but it's just incorporated into the operating system, so it allows the user interface to be more responsive. So basically what it does, it reduces the number of what we call context switches. So going from this thing to going to this thing, swapping pieces of software that's required for the GUI to perform its output functions. And our modular operating systems separates the graphic subsystems from the kernel and the operating system, but they work very much together. In the 1980s, Unix and VMS and many others had operating systems that were built that way. Linux and Mac OSs are also built that way. If we look at modern releases of Microsoft Windows or some of the earlier Microsoft Windows, they implement a graphic subsystem for the user in the user space. Graphics drawing routines, versions between NT4, Windows Server 9 exist mostly in the kernel space. So it's moving more and more towards the operating system, which means the operating system and the user interface work very closely together. And in Windows 9 and since then, there's little distinction between the interfaces and the kernel, one and the same thing. So many computer systems now allow the user to install or create any user interface they desire. With Windows, you get your standard user interface, but then when we have things like GNU and Linux and Unix, you had the GNOME, which was taken up quite a lot, although not generally tended to be used because it tends to be more command line. And graphical user interfaces have evolved over time, and they will continue evolving over time. And I think the thing to take away from this is that it might not necessarily be graphical anymore. It might be more spatial as we move on and we go to virtual reality and augmented reality. So you can see that that's actually going to change. So Windows certainly has modified its interface every time a new major version of Windows has come out. And likewise, the Mac OS GUI changed dramatically with the introduction of the Mac OS X in 1999. And it's a constantly evolving field. And as we interact with computers more differently, as we have touch screens, as maybe we have the Google glasses or Apple glasses that are supposed to be coming along soon, you will see that we react and respond with our systems in different ways that we might not call them graphical anymore, but more like spatial. But these will certainly develop and evolve more over time. So there you go. Quite a lot there that we've spoken about. You know, we've covered a lot of things there. Tried not to get too much into depth, but hopefully now you understand some of the things that go on inside the computer. What the kernel is, how program execution is dealt with, what interrupts are, talked about memory management, virtual memory, multitasking, disk access and file management, what device drivers are and what they do, looking at networking, security, user interfaces, and finally we talked about graphical user interface, but watch this space. So I hope that's given you a nice gentle introduction into some of the jobs and the important jobs that an operating system carries out.